So let me. So good afternoon, everyone. Um, Today is the third lecture in our series, Introduction to Homological Algebras. Today's lecture is going to be talking about natural transformations. Last week we had a discussion on functors, and functors are mappings between categories. So we have defined in our first lecture the concept of category being a generalization of most of the algebraic spaces or mathematical systems. And then we introduced in the last class the notion of functors. And then we say functor is a mapping structure preserving maps between categories. So today we are going to yet again introduce another concept, the concept of natural transformation. And here natural transformations will be uh, transform mappings between functors themselves. So functors are maps between categories, and then we will still have mappings between functors. If you have two functors, then we have transformation of functors. One functor can be transformed into another functor. And the concept is the concept of natural transformation. So as we have mentioned earlier, the material, we have one reference material for this course, and it is an introduction to homological algebra by Joseph J. Rothman. This book is published in 2009, and it is available online. Uh, so one can access the book free. You can download it and go through. So as I have said, the topic of this lecture is natural transformations. So just as homomorphisms compare algebraic structures, and we have two algebraic structures, we can define homomorphism between them to be a mapping from one structure into the other structure. And this map will preserve the composition or the binary operation or the structure preserving mappings are normally called homomorphisms. If you have groups, then you compare groups via a homomorphism. And then likewise, we talked about functors last week. To compare categories, we use the notion of functor. Now, if you want to compare functors, you have two different functors between two categories. You can compare the functors by making use of natural transformation. So the formal definition of a natural transformation is given here. If you have two functors, f and g, from a category C into another category D, covariant functors. The notion can also be defined using contravariant functors. We defined the notion of contravariant functors last week. Uh, and you obtain contravariant functors by just reversing arrows using opposite category over here. So you can refer to that lectures and see what we mean by covariant functors. So if you have two covariant functors, f and g, from C, a category C to a category B, a natural transformation is a alpha from F to G is actually a family of morphisms. So it is a family of morphism alpha A from FA being the image of an object A under the functor F, to G of A, and G of A is the image of an object A under the functor G. So if you have a family, all this family alpha A, as you run over all the objects in the category C, then that collection of the family is what we call natural transformation, subject to satisfying this condition here. So this is called the naturality condition, that for every morphism from A to B in the category C, the composite alpha B composed with F of F should be equal to Fg of F composed with alpha A. This is happening in the category D, that is the output category. So this condition is what we call the naturality condition. And this alpha, the members of this family, which we call natural transformation, are called components of the natural transformation. And two natural transformations are said to be equal if their corresponding components are equal. So if you have another natural transformation beta, which will be beta A from f of A to f of g of A, then those two natural transformations will only be equal if you equate corresponding components. So we can, I tried here to give you a picture of what a natural transformation is so that we can visualize what goes on. We try to see a visual version of what the naturality condition is all about. So you have a category and C and another category D here. And then you have two functors. The two functors, one functor F will map every object in this category to a new object in the category D. So A will be mapped under the functor F to f of A. And that object A will also be mapped to G of A under the functor G. But then again, if you have a second object B, it will be mapped to f of A by f, to f of B by f, and to G of B by the functor G. And then every morphism will also be mapped by these functors. So the morphism f from A to B will be mapped to a new morphism from f of A to f of B by the functor f, and then the image of this morphism is now f of f. And likewise, that morphism f will be mapped to the new morphism between the image of A and the image of B under the functor g here. So we say that a natural transformation from this functor f to the functor g will be a family, a collection of morphisms in the category, this morphism alpha A. So alpha A will transform f of A to g of A, and alpha B will transform f of B to g of B. So if you get hold of all these collections of these morphisms that transform from F to G, it's called a natural transformation, provided this square is commutative. This square is called the naturality, the square. That is what is actually depicting the natural condition. In other words, by commutativity, we mean if we compose alpha A with G of F, it should be the same thing as the composite F of F with alpha B. So uh, that is the requirement for a natural transformation. The definition is very simple, actually, only one requirement, that this composite should be equal to that composite over here, meaning the square must be commutative over here. So that is what we mean by a natural transformation between functors. So what we are going to do here is to try to form a very large category where the object of the category are functors, and the morphisms in that category will be natural transformations. So we have to find a way of multiplying natural transformations. So, but there is a natural way of multiplying this natural transformation. So the natural transformation actually can be multiplied, because if you have a natural transformation from F to G, and another natural transformation beta from G to H, then you can multiply alpha and beta together by multiplying the corresponding components of this natural transformation. So this is how the product beta after alpha is defined. So beta after alpha will now be a natural transformation from F to H. Remember, alpha is from F to G and beta is from G to H. Then you can now transform directly from F to H via the composite beta after alpha. So the composite beta after alpha will transform the functor F to H by this rule, that that is the component of the composite beta alpha of A, or sub A, should be equal to beta sub A composite alpha sub A. So what you do is to multiply the individual components. You have a way of multiplying morphisms in the category D. So you can just do the multiplication. This picture is to demonstrate how the composite is done. you have an object A, and then it is transformed. You have, so if you are to do a composition of natural transformation, you must have at least three functors. So I have a functor F and another functor G and a functor H, and each one of this functor is transforming A, is mapping A, the object A, into the category D. So this object A is mapped to F of A by the functor F, and it is also mapped to G of A and also mapped to H of A. So a natural transformation will transform F of A via alpha of A to G of A. And then we have another natural transformation, beta, whose component will map G of A in D to H of A. So by product, or by product of this natural transformation, we mean the composite of alpha A with beta A, and that composite will transform F of A directly to H of A. So if we do this, then we have a way of multiplying natural transformation, two natural transformation, to get a new natural transformation. So once we are able to multiply natural transformations, then we can now see that we can form a category whose objects are now functors, and the morphisms will be natural transformation between functors. So thus will form the arrows in a category, and it is going to be a very large category. We call it a functor category. But then one of the another requirement that is needed in the definition of a category is the presence of identity. So we can always, given any functor f from C to D, one can always define the identity natural transformation omega f, which is now a natural transformation from f to f, by setting the component omega f sub A. This will form the component to be f of A to f of A, to be a mapping, the morphism from f of A to f of A. And this morphism is declared to be the identity morphism on f of A. So once you declare every component of the natural transformation omega f to be the identity morphism on its domain and image, then you have identity natural transformation. So this will serve like the identity morphism in the functor category. So now this means with this identity morphism and the composition we have described, we can now define a large category which we call functor category. So which means if you have C to be a small category, so there is a small requirement that here C should be a small category. And we know what is a small category. We have defined it in our first lecture. It is a category in which the collection of objects is a set. So that is called a small category. If it is not small, it is called a large category. So if C is a small category and D is any category, can be large, then the functor category, which is denoted by D to power C, this will be the collection. That will be a category whose objects are functors. So all functors from C to D will form the object in this category. And the morphisms in this category are natural transformation between functors. So now we see in this category we have a composition law, because we have just said here that we can multiply to natural transformations. And once we are able to multiply natural transformation, we have a composition law. And this composition law, it is clearly associative, because composition in D is associative. And so therefore, and we have the identity natural transformation here. So therefore, this is actually a category. So D to power C is a category. It is called a functor category, given the fact that the objects in this category are functors. And so therefore, it is called a functor category. I give you an example here. If you take, for example, in this definition, you take C to be Z. So if you view the set of the set of integers as a category under the reverse partial order, you remember we talked about this. They are viewing Z, giving it a partial order, where you say n plus 1 is less than or equal to n. So this is a reverse order, 2 is greater than or equal to 3, and 3 is greater than or equal to 4, and so on. So if you give the set of integers that structure of a partially ordered set using the reverse order, then you have a category that the set of integers can be viewed as a category. And then seeing that as a category, you can now look at the functor category, up to power z, and this will now be the category of all functors from the set from z to the category of abelian groups. Ab actually is the category of abelian groups. Object here are abelian groups, and morphisms are group homomorphisms inside the ab. And so therefore, every functor, in other words, every object in this functor category is actually a sequence. Will just can be viewed as a sequence of abelian groups with abelian group homomorphisms in between them. So an plus 1, and then fn plus 1 to an, which means it is a sequence of homomorphism of abelian groups. And that is how we view functor in this category. Such a sequence is called a chain complex if it satisfies the condition that the composite of any two uh, subsequent homomorphisms is 0. So if I compose fn plus 1 with fn, and I always get 0 at every stage of the sequence, then the chain is called a chain complex. The sequence is referred to as a complex or a chain complex. Now, in that category, the natural transformations between functors. So you see this sequence at the top here, an plus 1 to an minus 1, this is a functor. And that sequence down there, bn plus 1 to bn minus 1, is again another functor. So we have just said that functors in this category are viewed as sequence of homomorphisms, of abelian group homomorphisms. So if you have one sequence at the top here and another sequence down there, then you can talk about a natural transformation from this sequence at the top to the sequence down there. And then a natural transformation is yet again another sequence of morphisms, homomorphisms again. It's a sequence of morphisms from an to bn for all n in the set of integers, which make this diagram commute, because this is the diagram has to be commutative by a naturality condition. That is the natural, because these are natural squares. So fn composed with alpha n minus 1 should be equal to alpha n composed with gn. And then fn plus 1 composed with alpha n should be alpha n plus 1 composed with gn plus 1. So at every stage of these squares, all these squares are commutative. So the entire diagram is actually commutative. So this is how we view a natural transformation in the functor category up to power z. And then natural transformation between chain complexes is called a chain map. Actually, there is a topological motivation to this type of construction, and I think that is the motivation to studying homological algebras. Actually, it started from looking at topological spaces and defining complex structures, uh, uh, complexes on topological spaces. But then we are going to come to that issue. So here, so we see an example of a functor category. So in functor category, the natural transformations are morphisms, and then we know the definition of a morphism when we say a morphism to be an isomorphism. So if you review a natural transformation in the functor category and it happens to be an isomorphism there, then you say it is a natural isomorphism. So this is why we say a natural isomorphism is a natural transformation which is an isomorphism in the functor category. And in this situation, if there is a natural isomorphism from a functor F to a functor G, then we say they are naturally isomorphic. And we write F is naturally isomorphic to G using this symbol here. And So we have a theorem, and which will be the only theorem we will prove today, to say that given two functors from C to D, then a natural transformation between the functors is a natural isomorphism if and only if each of its components, alpha A, is an isomorphism in D. Components of the natural transformation are morphisms in the category D. And so if each of the component is already an isomorphism, then the natural transformation will automatically be a natural isomorphism. So let us see this proof here that so if we suppose alpha is a natural isomorphism, it means it is an isomorphism in the functor category. So if it is an isomorphism in the functor category, then you have another natural transformation. It means it has an inverse. So there is a natural transformation beta from G to F, which is the inverse of alpha now. And so therefore, if you say alpha beta, this should be the identity on G, because alpha after beta should be the identity. It means perform beta first. Beta is from G to F, and then alpha from F to G. So since beta is the inverse of alpha, this should be equal to the identity natural transformation. But then if this is the case, if this natural transformation is equal to the identity natural transformation, then the component must be equal for all A, because we say a natural transformation is two natural transformation are equal if and only if the corresponding components of the natural transformation are equal. So therefore, given any object alpha of A, alpha times beta sub A should be equal to omega G. Omega G is the identity natural transformation sub A, of G actually. And then, but by the way we define composite of product of two natural transformation, this is alpha A times alpha B. And the definition of the identity natural transformation is that it is the identity morphism on G of A. So that means alpha beta of A here is acting like the inverse of alpha of A, if you look at it very carefully, even though you have to have the reverse equality also, where you say beta of A equal to alpha of A should be equal to the identity of on F of A. But this is also the same type of actually it's the same type of observation. The same kind of observation will amount to having this product to be equal to the identity morphism on F of A. And this equation, with that equation, pronouns that beta of A is the inverse of alpha of A, which means every component is having an inverse. And so therefore, alpha of A, each component for every A, alpha of A is an isomorphism in the category D. So which means if the natural transformation is an isomorphism, then every component will also be an isomorphism. Then we can look at also the converse. If we suppose each component of the natural transformation is an isomorphism with inverse beta of A, then it means given F, because we are saying alpha of A are the component of the natural transformation, and we now want to show that the natural transformation is an isomorphism, then by the naturality condition, the natural square must be commutative. So this square must be commutative in the sense that G of F after alpha of A should be equal to alpha B after F of F. So this equation must hold. And so therefore it means beta y of, so if you take another morphism, y, I think this should be B. This should be B. Beta of B composed with G of F should be equal to beta of B composed with G of F. So using this, actually this condition here, you can see that since this is happening for all alpha, So you can also use beta, and then you have this equality, and uh, and you can now see that um, using the commutativity of this diagram over here, we have beta of b g of f to be equal to beta of b g of f multiplied by or composed with one. This is the identity morphism on G of A. So because this is a morphism from G to G, so if you compose with the identity from G of A to G of B, if you compose with the identity, it is actually that morphism. So this is just like adding the identity over here. But identity morphism is alpha of A composed with beta of A, given the fact that beta is the inverse of alpha. And so therefore, but G of F composed with alpha of F commute. By the commutativity of the diagram here, you can replace this with alpha of B composed with F of F. And so that is what we did here. So we use this actually equality over here, and then we have this. But beta composed with alpha is identity, because beta is the inverse of alpha, and then you have F of F composed with beta of A, and that means FF composed with beta of A. So which means this diagram here, because what we have seen here, this is beta of B. I said this Y should be B. Beta of B composed with G of F. So if you look at beta of B after G of F should be equal to F of F after beta of A. And this is actually what we have here. So this equality we establish here establish that this square is commutative. And so therefore, if this square commutes, then we can define a natural transformation whose component are this beta. So with the component beta, and this natural transformation defined with the component beta will clearly be the inverse of A. So therefore, or the inverse of alpha, and which means the original natural transformation alpha has an inverse. So that means if all the components of a natural transformation are isomorphic, then the natural transformation itself will be naturally isomorphic. I will be an isomorphism if the components are isomorphism. So we have an example here to show that the home functor. You remember home functor? We define it. That is a functor that you can define from any category into the category sets. So if you take any point, a fixed point, actually, just fix a point and define home functor. The home functor, that is sending every object. So if you have any set, you send it to the set of all morphisms from this singleton into that set A. So this home functor defined in this way, where the target is always singleton, is naturally isomorphic to the identity functor on sets. And to see this, we can see that if we want to see that it is naturally isomorphic to that, we can define a natural transformation from this home functor to the identity functor, functor on sets, and show that that natural transformation is an isomorphism. And so this is what we did. So what we did here is to define component of the natural transformation alpha A. So if you take alpha A, and it will now be from the image of A under this home functor. An image of A under the home functor is home of the singleton, comma A. This is the set of all morphisms from the singleton into A. And then you map it to A, because A is the image of every object under the identity functor, because identity functor is fixing every object and also fixing every morphism. So if you define the alpha of A by this alpha of A of F to be equal to F of X, because you know members here are morphisms. So this will be a morphism from X into A. This F is a morphism from X into A. And then you now map it to its image in A. You have only one way of defining a mapping from a singleton into another set. There is one and only one way of doing so. And so therefore, this mapping is actually uh, invertible. It is invertible. It is clearly a bijection because this alpha of A. And so, since it is a bijection, we can define a natural transformation by using alpha of A as the component of the natural transformation. So we define a natural transformation with component alpha of A, and then we show that this is actually indeed a natural transformation. If we take the collection of all this alpha of A, we need to show that it is a natural transformation. In other words, you have to check that this square is commutative. This is the naturality square. We have to show that the square is commutative. So, and to see that this square is commutative, this is easy because we can just consider this square and see that if you go clockwise like this, then it means you are saying alpha beta alpha b after this mapping home of F. So if you compose this with that, this is this composition. But you know, this mapping, this home of the singleton comma F is a mapping from this home set into the home set of B. So therefore, it acts on a map from X to A because these are morphisms from X to A. So this H is a map from X to A. And so therefore, the home functor, this is actually the induced, we have talked about this thing in our last class, the induced morphism. So the way this home functor is defined is to compose F with H. So this is F with H. That is the induced morphism. So the image of H under this home, it is FH. But then alpha beta of FH is FH of X by the way we define alpha of A, this component. We just say the map, if you are, if alpha B acts on FH, then it is going to be the image of X under FH, the composite. But that is equal to F of H of X. And H of X will be the image of alpha A, image of H under alpha A. And that is equal to F alpha A of H. So since this thing is happening for all H, for every H from this home set, it means alpha B after this home, so alpha B after the home here should be equal to F after alpha A. So it should be equal to this F after alpha A. In other words, this line here is proving that this square is commutative. So since this square commute, it means this alpha we have defined here is actually a natural transformation. And so therefore, we define a natural transformation using components that are bijections, and bijections are isomorphism in sets. And so therefore, this natural transformation is an isomorphism, and then we have established that the home functor whose source is always a singleton is naturally isomorphic to the identity home functor, to the identity functor on sets. So that is an exemplification of the concept of natural isomorphism, actually. So we say if a functor, that is a covariant functor, but the concept can also be defined on contravariant functor. So a covariant functor, F from C into sets, so from any category into the category of sets, is called representable if there exists an object such that that functor is naturally isomorphic to the home functor with respect to the object. So any functor that is naturally isomorphic to the home functor is called representable. So I close this lecture with a remark which will be the starting point of our next lecture, um, because we have been talking about functor category. So we define the functor for category to be the category whose objects are functors. And then the morphisms are now natural transformations, which means given any two objects, F and G, which are now functors, the Hom set, that is the set of morphisms between F and G, should be the set of all, the collection of all natural transformations from F to G. And this is the set of morphisms. And you remember in our definition of category, it is required that all Hom set must be a set. The all or the collection of Hom set of all morphisms between any two objects should be a set. This is what we require in the definition of category. But in our definition of functor category, D to power C, actually the it's not always the case that this thing is a set. But the restriction we put that C is a small category is necessary to ensure that the Hom sets are actually sets. So that restriction cannot be removed, because if C is not a small category, the collection of morphisms between objects F and G may not be a set. And that is in violation with our requirement for defining a category. We require that the collection of morphisms between any two objects must be a set. And so, to remedy that, we put the restriction that C must be a small category. But then in the next lecture, we shall talk more about this set of morphisms between functors, that is collection of natural transformations between functors. And we are going to prove a result that is known as Yoneda lemma, showing that if the source here, F, if F is a Hom functor, then not F comma G is always a set, which means if you are considering set of all collection of all natural transformation from a Hom functor into any other functor, that collection will always be a set. And that lemma is called, that result is called a Neda lemma, and it will form the subject of our discussion in the next lecture. We are going to prove that lemma, and we'll look at some consequences of that Yoneda lemma. I think this is where I stop. Thank you very much for your attention.
Very much
Thank
for
you, sir.
Thank you very much, sir, for this wonderful presentation. Really appreciate.
thank you, sir, for this remarkable presentation. Okay, thank you very much, sir, for your beautiful presentation. So, like
Like
to
to
we would like to call on the online participant for comments and questions. So I think we have Dr. Diko here. Please, you can mute your mic if you are speaking or you are mute yourself. Okay.
Okay. Good afternoon, everybody. Yes, good afternoon to the speaker.
Good afternoon.
I'm very happy to be here. First time in group, I can see that the lecture series started last week. I'm so
Yes.
unfortunate that I missed it. I would have loved to be here. So, Dr. Imam, thank you for the lecture. You know, I would have loved to be here anyway. So,
Yes.
yes,
Yeah. So,
yes. Um, like I always say, I can see that you gave examples in some of the representations that you have, but maybe because I missed the last lecture, there are some things